Before we can construct a simple spring oscillator, we'll need to determine the spring constant for this spring. To do so, we will hang the spring from the table clamp and stretch it using this force sensor. We know from Hooke's law that there should be a linear relationship between the displacement of a spring and the force provided by the spring, and that this relationship is characterized by the spring constant K. To experimentally go about finding this K value, we'll start by applying a small displacement to the spring so that we can align the top of the force sensor with a mark on our 2-meter stick, and then zero the force sensor at this location to make our spring displacement relative to this mark. Now we can continue to stretch our spring more while recording the force and correlating this value with a displacement relative to that initial mark on the 2-meter stick that we selected as our 0 point. Once we have collected a total of 6 measurements, we will perform a least squares best fit calculation to determine an averaged value that will represent the spring constant for this experiment. Once we have determined the mass of the spring, we'll now sort of invert our setup from the previous procedure by attaching the force sensor to the table clamp and hanging the spring from the hook of the force sensor. We'll also make a small adjustment to the sampling rate of the GLX, and this time we want it to display a plot of force versus time, so we'll navigate to the graph screen. Now we can add a hooked mass to the other end of our spring and pull down lightly to begin the oscillations. Care should be taken to ensure that the spring is not overextended and that the oscillations are completed smoothly. Moreover, small oscillations are just as effective and somewhat less error-prone than larger oscillations. Once the spring oscillator is moving constantly, the play button on the GLX may be pressed so that the data logger will start collecting measurements. Allow at least 10 cycles to be completed on the GLX before stopping the logging process by pressing the play button again. Using the cursor on the GLX, determine the time difference between the first and the 10th oscillation. This will be used to determine the period. Once another trial is completed with a different hanging mass, additional calculations can then be completed to compare the experimental period to the theoretic period based on the spring constant value previously determined. To utilize the pendulum in this third procedure, we'll unwind some length of string from the hanger and measure the diameter of the hanging mass using the vernier caliper. The length of the string should also be measured from the top of the pendulum hanger to the top of the ball. The total length of the pendulum will then be the length of the string plus the diameter of the hanging ball. The pendulum may be started by slightly raising the height of the ball and then releasing it. However, in order for the small angle approximation theory to be applicable, which is used in some of the calculations of this experiment, the angle of release for the pendulum should not exceed 5 degrees from the vertical. This is probably less than you would expect, but just like the spring oscillator, small oscillations are just as effective and much less error-prone than larger ones. Once the pendulum is oscillating unabated, the time to complete 30 oscillations should be counted using a stopwatch. Keep in mind that the time for one oscillation represents the time it takes for the pendulum to leave a point in space and then return to that same point again. By dividing this total time for 30 oscillations by the number of completed oscillation cycles, a more accurate period for the pendulum may be determined. This process should then be repeated for 5 additional pendulum lengths. By plotting the period squared by the pendulum length, the slope of the line can be correlated to determine an experimental value for local gravitational acceleration. Notably, this method for determining local gravitational acceleration is both very effective and one of the first methods developed for doing so accurately.